And hi, good afternoon again to folks just joining. So I will keep an eye on people just entering the space. And I'll go ahead and just give a kind of a background introduction to our conversation today. So hi, everybody. Hope everyone's doing well. We are going to have our second internal session here today. I'm really excited to learn about biochar. Sorry, I'm continuing to add people in the background here. And I just want to quickly remind everybody that we are recording this session, but the kind of conversation part will be not recorded at the end. So feel free to, ask all sorts of questions, have a little conversation at the end. One thing to note that's different from our regular learning exchange series is that you're welcome. Actually, we're encouraging you to just save questions for the end, and then we'll have a discussion. So don't. We're not going to have the same kind of format. We're going to have one of our guests facilitate the Q&A. So they're not going to be keeping track of a chat, or there's no Q&A tab. So feel free to save your questions, and then we'll have a nice conversation at the end. And I'll remind anyone if we have activity in the chat to just kind of keep it in the conversation. And so with that, I'll hand it over here to get introductions for our speakers today. And I'll handle the recording in the background. Thank you.
Great. Well, good afternoon, everyone, and thank you for joining us. I'd like to offer a special thank you to Lauren and to Steve Thompson at the National Center for Appropriate Technology for this invitation today. My name is Beverly Paul, and I'm helping to coordinate stakeholders in a task force we're calling the Biochar Policy Options Project. I work for a small agriculture-focused firm in Washington, D.C., but I'm joining you today from Miami. Our panelists are very well known to many of you and highly knowledgeable in this field. First, Gloria Flora directs Sustainable Obtainable Solutions, SOS, a nonprofit ensuring the sustainability of public lands. She founded SOS after 23 years in Forest Service leadership. Gloria founded and directs the U.S. Biochar Initiative. She's joining us from Northeastern Washington, where her internet service is not great, so she won't have her camera on today. And Nate Anderson is a research forester with the Rocky Mountain Research Station of the U.S. Forest Service in Missoula, Montana. He's conducted biomass and biochar research since 2009, and Nate is joining us today from Cleveland. We will each make short presentations, and then we're going to open for questions. So at this point, I'm going to just turn it over to Gloria, and thanks again for the opportunity to be here.
Thank you very much. Appreciate the opportunity to speak with you all about biochar, one of my favorite things in the world. And not being clear on exactly everyone's knowledge level, I'm going to take us from very elementary into complexity. But bear with me, and there's plenty of time for questions at the end. So I want to talk to you today about biochar as an elegant solution for complex problems. And the complex problem that we're facing right now is climate change. That's essentially from too much CO2 and other greenhouse gases in the atmosphere. And each of these 6 points are part of that complex problem. But as we go through this presentation, you'll see that I'm showing you how biochar relates to each of those 6 points and helps address that problem. Number one, excess CO2 from burning fossil fuels, methane from livestock landfills and biomass decomposition, nitrogen, phosphorus runoff, and nitrous oxide off-gassing from fossil fuels converted to fertilizers in agricultural fields. We have temperature and moisture regimes that are changing and not on a steady track, a trajectory, but rather with spiking perturbations, and that's very deleterious to plant health, and it also benefits the diseases and insect life cycles that attack plants.
Hey, Gloria?
We have concentration. Yes?
I'm not seeing your slides. I'm not sure if others are seeing your slides or not, but if you have shared your slides, at least one of us can't see them on the screen.
Okay. Thank you for stopping me. I'm clicking on all kinds of buttons here. I hope you are enjoying my phone number.
I've got your screen now, and if you go to your presentation mode, it should pop up.
Okay.
Yep.
There you go.
Perfect.
How's
You got
that?
it.
All
got it.
right. Well, then you can just watch as I flip through and get you up to the right slide here. This is what I was talking about, these complex problems. Concentrations of biomass waste, agriculture and forestry, and high forest density that increases wildfire risk. So let's focus on biochar and look at the climate benefits, which are not just carbon sequestration, but there's a lot of things associated with biochar that do provide climate benefits. Biochar is simply charcoal, but it's charcoal with a purpose, and the purpose is either to support the soil biology and nutrients, or protect that biology from heavy metals and toxins. And one of the primary functions that biochar, or how biochar performs these primary functions, is much to do with the surface area and the porosity. As you can see on the right-hand side, is a close-up of biochar, and that surface area is absolutely phenomenal. You can have hundreds of square yards of surface area in just 1 cubic centimeter of biochar. And that surface is very active because it has a very high cation exchange capacity. So biochar is carbon. It lasts hundreds of thousands of years in the soil. It can be carbon neutral or carbon negative, depending on a lot of different factors, and Nate will be covering a lot of those factors. It's carbon with amenities, though, because of that negative cation exchange capacity that biochar has. Because of that surface area, it can attract and hold nutrients, attract and hold gases that are important greenhouse gases, particularly when we see like CH4, that's methane. And methane is about 30 times more intense in terms of its effects on the atmosphere than CO2. And likewise, nitrous oxide, which is 300 times more, has a more impact. What you'll hear us talk about as we go through this slide is carbon dioxide equivalent, CO2e. And so that's bringing all those greenhouse gases into one common metric. Biochar also attracts and holds water, and that's very significant. What kinds of biomass can be converted into biochar? What can we take out of the waste stream and convert to a valuable product? Well, there's quite a few things. As long as they're clean and organic, you could use industrial residues. You can use, a big one is forestry crops residues, and including urban wood waste, which is in excess of the total amount of slash that comes off national forests from forest management activities. So we're not talking a small contribution here. Agricultural crops and residues. And what we focus on in agricultural crops and residues are the woody residues. We don't really want to convert things that could be composted into biochar. We want to focus on those woody residues that are difficult to compost. Sewage has been talked about. I question that because of the, we're actually little hazmat units walking around in skin. We have so many chemicals in our bodies that it's really questionable whether all of those would be eliminated through pyrolysis. And municipal solid waste, we never want to use that because we don't know what's in that waste stream. But animal residues, algae, digestase from the result of creating algae biofuel, that can all be converted to biomass or biochar. And biochar, this is just a quick graphic to show you where that carbon from the biomass goes. If we enter that biomass into a pyrolysis unit, which is just an oven which has very limited oxygen and high temperatures, the result that comes out is the biochar retains 50% of that carbon residue, whereas the rest of the carbon can be captured in biofuels, bio-oil or hydrogen. The residual heat is also a process or a process result. Biofuels can also be grabbed and put back into the pyrolysis process, because these emissions from the thermal conversion of this biomass are very valuable, actually. There's hydrogen and there's carbon monoxide and other combustible gases that can help feed the process if you cycle them back. So what we're talking about when we're taking this biomass and reducing it through pyrolysis is we have a 50% carbon loss and a 75% biomass or mass loss, but we end up with biochar that has a 75 to 90% carbon content. And I'm going to speed it up here because I don't want to get too far in the weeds, but pyrolysis, gasification, even open burning in a controlled oxygen environment can still bring you a lot of benefits. If you're in a controlled environment such as pyrolysis, you can get syngas, bio-oil, and heat. These are all non-fossil fuel energies. That has a climate benefit. Additional climate benefits are the biochar with carbon sequestration, the soil amendment, the less NPK fertilizer use as a result of that biochar holding the fertilizers in the soil, the greenhouse gas capture carbon credits, reducing waste, which would otherwise decompose and contribute to more emissions. And the emissions from the process are captured and recycled or used as much as possible. And you can have full circle solutions where your heat and from a pyrolysis unit is pumped into a greenhouse, your gases are converted to electricity, and your biochar that comes out of the pyrolysis is put back into the greenhouse to improve the soils in the greenhouse. Emissions, this is an actual emissions from the University of Montana Biomax system, which is a mobile pyrolysis unit. And as you can see, it complies with the California air quality standards, which are the highest in the nation. Okay, let's talk about biochar and what we were actually doing when we put biochar together with soils, plants, and animals. As I mentioned earlier, biochar in the soil grabs and holds nutrients in water. It has a high pH. It can help with soils that have become acidified from over-fertilization, over-chemical fertilization. It improves soil texture, the tilth, the fluffiness, if you will, of soil because of its ability to get in between the platelets like of clay and puff them open. The carbon we've spoken about, the greenhouse gas capture and reduction. Biochar can reduce nitrous oxide off-gassing from soils by 50 to 80% for at least 3 years, probably longer, but the research only went 3 years, so that's all we're willing to say. The other thing about the biochar, you notice the porosity of it. Those little pores provide excellent habitat for microbes and mycelia, which are very important in the nutrient exchange process with root hairs. So biochar and compost, wonderful combination. We'd love to see those put together because of all these benefits. Just adding 10% by volume, you capture your off-gassing and nutrient runoff. It reduces odors, helps distribute the moisture through the production pile. Because it's dark, you absorb more radiant heat from the sun. The compost charges the biochar with nutrients, so that you're sure that you have a charged biochar. Biochar in and of itself is a soil amendment, not a fertilizer. It needs to have fertilizers or nutrients added to it so it can absorb those and then make those bioavailable to plants. And it enhances soil fertility long term. Remember that hundreds of thousands of years that it stays. Here's one example of improvement in crop production. No biochar, 8 tons per hectare and 20 tons per hectare in a cornfield in Colombia. And I will say you don't always get this kind of shocking productivity increase. The worse the soil, the better the biochar reacts and the better the plants react to the biochar. But it still has a lot of other benefits besides this high visibility plant and productivity improvement. And plants absorb CO2, and increasing primary productivity increases CO2 sequestration in the plants themselves. So biochar and livestock, beautiful combination here. I use this all the time on my farm. We add biochar to the chicken litter. It reduces the odor, captures the ammonia and nitrates, increases the efficacy of the composted litter, and we feed biochar to our ruminants. They biochar just by 1% volume in their feed will reduce methane emissions by 50%. And this is my ox, Hercules, and I can tell you his methane emissions are impressive. So that's why he gets biochar. So how do we move carbon out of the active cycle when we're talking about something like carbon sequestration? Simple graphic here. Carbon is present in two cycles, one the active, one the inactive. In the inactive, we're talking about the lithosphere carbon store, all the rocks, fossil fuels, et cetera, and biochar that are in the soil that are there long term. The active cycle is constantly in motion between oceans, forests, grasses, grasslands, organic matter, us. So what we want to do with biochar is remove carbon from the active cycle and put it in the inactive cycle. So does it really last that long? Well, research shows us that biochars are highly recalcitrant in soils with half-lives of 100 to 900 years. We know we can find biochar, great deposits of biochar in the Amazonian jungle that go as far as 6 to 8 feet deep. Amazonian Indians were putting biochar on soils for hundreds of years, if not longer. The biochar being dated from those soil pits in the Amazon are over 2,500 years old. So we know it's recalcitrant, but we know to prove it, this research shows that we can provide a credible carbon sink, because if we have a half-life of over 80 years, it counts as a long-term carbon sequestration solution. This is getting into the weeds a little bit, but I want to show you the difficulty of calibrating or calculating how much carbon benefit biochar actually offers, because you can do the statistics. You can focus on ag and grasslands, you can focus on forest, you can do a combination. But you see, with biochar, it has a lot of benefits, certainly not as much as some of these above here in forestry in and of itself, but biochar doesn't operate in and of itself. Biochar plays an important role in reforestation by improving forest soils. It plays a role in natural forest management, in that the slash that's generated from all the forest restoration work that is happening right now to reduce forest density that have become unnaturally dense because of the exclusion of wildfire for over 100 years. Throw in the gasoline and match of climate change, and those fuels will burn. That's why we're seeing such catastrophic wildfires. So biochar is a great way to use the slash that's created from this forest management, improving plantations, likewise improving the soils, and fire management. We're removing the undergrowth and doing something smart with it rather than leaving it on the ground or just piling it and burning it in an open burn. And when we look at agriculture and grasslands, biochar plays an important role in nutrient management. As I mentioned, the capturing of nitrogen and phosphorus is really, really important. One, it's a commodity that farmers have to pay dearly for. Secondly, it's highly mobile. Nitrogen and phosphorus love to rush off to the nearest stream. When nitrogen and phosphorus get into streams, they encourage algae and plant growth in those waterways. That removes oxygen from water. Fish and aquatic life need oxygen, and so they are deprived because of the increased nutrients, and that's why you have dead zones at the mouths of almost all major rivers of the world that go through any kind of agricultural land, is because those nutrients have left the land and gone into the water, much to the dismay of the aquatic life. So if we can capture and hold those nutrients on the land, we are doing a good service all the way around, not only to aquatics, but also to our agriculture efforts. I've mentioned the grazing, the biochar in the food, improving not just the methane emissions, but also the overall health. Remember that we take charcoal when we ingest a poison or aren't feeling well, and it grabs those poisons and removes them from our system. Conservation agriculture, biochar plays a really important role, particularly in no-till agricultural practices, and even improving rice, because biochar added to rice paddies can significantly reduce the methane decomposition and provides a wonderful methane sink. And then in wetlands, I've already mentioned the aquatic benefits, but also biochar is used in coastal restoration because it has a high pH. We have acidic oceans, and those acidic oceans are negatively affecting shellfish production, and as well as natural aquatic life. And so if we can raise the pH by adding biochar, it's also helping to reduce the impacts to coastal life. So if we want to get into specifics on and use numbers, we can do that too. These numbers are taken from Project Drawdown, which is billed as the most comprehensive plan ever proposed to reverse global warming through natural solutions. And it's absolutely fascinating. I encourage you to look at that in more depth. There are hundreds of solutions, and they're all life benefiting and not techno solutions that have a lot of negative spin-offs from them. But the work the Project Drawdown did in calculating the effects of biochar, they focused on agriculture in this one from crop residues. And so I'm not going to read through the numbers. They're here. You can see it on the recording later. There were a lot of limitations and factors that they worked into this. It does have an overall lifetime cost, but we're still drawing down an incredible amount of CO2e, the CO2 equivalents. So that's from a total life cycle assessment. There was a study done in 2010, which is viewed often as the holy grail of some biochar studies because it was so comprehensive in reviewing biochar's potential carbon drawdown, and it considered agriculture and forestry waste. And it came out, interestingly, right in the middle of that Project Drawdown's estimates of gigatons of CO2e sequestered over a period of 30 years. And offsetting on a yearly basis 12% of anthropogenic greenhouse gases. So let's take a quick summary of biochar benefits. And even though climate is in a separate category over here, all of these other benefits actually do help with climate as well. So we talked about renewable energy, heat and power, syngas and bio-oil. Bio-oil is an oil that's used in like a bunker fuel for shipping and for ships, and for also in concrete production or cement production. And it can be refined to biodiesel. It's a little iffy whether we're seeing a carbon neutral or carbon negative effect from that, but that's being worked on. Syngas has less BTUs than natural gas, but it still is a burnable gas. And so we're replacing fossil fuels in water quality, filtering toxins, holding heavy metals. I didn't even get into the uses of biochar as a remediation tool, but it is fabulous. It's being used extensively in cities in stormwater remediation. Capturing NMP runoff, raising pH, it's persistent as a soil amendment. You use less fertilizer, reduce your water demands. You can reduce your irrigation demands by 30% with biochar enhanced soil. Think about that. Less available water from natural sources because of all the drought and the more drought that's predicted, plus less irrigation required. Irrigation uses energy. Irrigation uses water that might have other positive uses downstream. So, and we're also increasing plant growth. So, and then the sequestering carbon, reducing greenhouse gas emissions by increasing plant growth again, and retaining soil moisture. So I'm going to check the time here. I think I've used my 20 minutes. I have some sustainability guidelines that I'd encourage you to look at after the session is available via recording, but I can sum it up by saying if it's not sustainable, don't do it. What we're addressing are complex problems as a result of doing unsustainable practices. So with that, I will release the screen and turn it over to Bev to introduce Nathan.
Thank you, Gloria. Nate, when you're ready, I think it's all yours.
Great. Thanks a lot, Bev. And thanks everybody for being here. Thanks for the invitation, Bev. And I also want to thank Steve Thompson at the National Center for Appropriate Technology. We've had quite a bit of discussion about biochar, and thanks for the invitation. Thanks everybody for being here. So, Bev, can you see my slides and hear me okay?
Yep, everything's great.
Okay, great. Well, without further introduction, I will just dive into it. I'm going to talk to you about some work we've been doing within the Rocky Mountain Research Station on biochar production, economics, and I'll also talk a little bit about policy implications with a focus on the forest sector. So I definitely know a lot of folks on this call want a better understanding of where biochar as a product with all its promise fits into the forest sector. So we'll talk quite a bit about that. I want to make some direct connections to what Gloria was talking about in terms of biochar systems, what are their potential benefits, and make a connection to the forest sector. I want to talk about bioproduct supply chains with a focus on forest biomass. So it will definitely be focused pretty squarely on forest biomass in the form of treatment residues, and manufacturing residues. And then I'll talk about the economics. I'm going to stay at a pretty high level in terms of the economics. I won't share much about financial models for specific biochar conversion pathways or biochar enterprises, although we've done a lot of work on that. But I want to talk about more broadly investment risk in biochar production, and then how we go about de-risking biochar ventures, especially when they are integrated with traditional forest industry. And I'll make a few policy connections. I'm not a policy researcher, but I think there are some really nice policy aspects to biochar, the forest sector. And then I'll leave you with some take-home messages, and later we have some time for questions and discussion. Before I get into the meat of the talk, I want to just thank the National Institute of Food and Agriculture at USDA for funding that we have had over the years with some pretty large projects through the Biomass Research and Development Initiative, and also through the AfriCap program. The Forest Service has also made some pretty large investments at different levels, from Washington office to the research stations to the regions in biochar and biomass research. And we've had a lot of help from our university partners, faculty, staff, postdocs, graduate students like these pictured here. So thanks to all of them. And none of this research would be possible without industry participation. So I definitely want to thank our industry partners and NGO partners as well. So biochar systems, as Gloria did a great job discussing, have some pretty fundamental core benefits. The soil benefits are paramount. And we also want to be very mindful of the waste management benefits associated, especially in the ag and forestry sector, with waste biomass, renewable energy. A lot of the conversion systems we use to produce biomass, produce biochar from biomass, have renewable energy benefits, heat, power, cogeneration, sometimes liquid fuel products, and then carbon sequestration and the climate change mitigation benefits from these systems. In the forest sector, we have kind of a really nice back loop here where we can provide forest biomass and potentially use biochar in systems like nursery systems, but also the forest sector as a consumer of biochar in forest restoration, in rehabilitation of roads and old mine sites and degraded sites, and resilience, especially, as Gloria mentioned, resilience to drought and the water holding capacity of soils, in this case, forest soils. So we have this really nice connection here, but by both providing biomass for biochar production and being a consumer of biochar out on the forest. Often in the forest sector, we're pretty obsessed with the biomass production side of this bioproduct supply chain. So that's the silviculture, the harvest and collection and processing. And once the biomass leaves the site, leaves the treatment unit, we kind of don't give much thought about where it's going. Maybe it's going to a boiler at a pulp mill, or maybe it's going somewhere else. In the biochar systems, we really need to be looking at the whole bioproduct supply chain and have a good awareness of the conversion technology that we're providing raw material for, and especially the end use. What's the end use of that char? Because what we provide on the biomass side impacts the quality of that char downstream. And I also want you to think about bioproduct supply chains as not just in their material flows, so the flow of wood fiber and the carbon that's in wood fiber from left to right in this chain, but also the flows of capital and where capital investment is occurring along this supply chain that includes all these different moving parts. And then also information, not just information about product quality, for example, at each stage, but potentially things like chain of custody and the carbon impact and life cycle of the products that we're producing. So this is the big picture, and we need to kind of break out of the really narrow focus on biomass production in the forest sector. So a lot of you on this call already appreciate some of the competitive advantages that forest biomass has over other biomass options like purpose-grown grasses or woody biomass feedstocks. We already produce a very large amount of forest biomass in the form of waste or byproduct from traditional timber management, forest restoration, fuel treatment. And this gives us options for material quality and costs. So we might be able to convert a really low grade hog fuel type material into biochar, or we might need a high quality clean dry microchip on the other end of the spectrum. We often can get this material at low, zero, or negative stumpage costs, and I'll explain a little bit more about what that means, negative stumpage costs, in a moment. But the idea is a lot of times these materials are kind of on the margins of the main solid wood product supply chain in the form of lumber or boards or cross-laminated timber, for example. And we have opportunities to co-locate biochar production with hardened industrial sites or reclaimed brownfield sites, industrial sites. That's a good opportunity in the forest sector, and it's often close to the feedstock we require. And forest feedstocks generally have a pretty good carbon balance in terms of sustainability and carbon, especially in situations where we're keeping land in forested land use under good sustainable management. And as all of you on this call appreciate, we have a whole bunch of other benefits tied to forest products, even if they're not compensated, even if they're public goods or ecosystem services in the form of carbon sequestration, recreation, clean water, biodiversity, and all these other things we come to expect from our forests. But forest biomass also has its disadvantages as a feedstock. We're often trying to collect material over large landscapes in difficult terrain with diverse, dispersed access, poor quality forest roads, long transportation distances, and this can translate into pretty costly logistics. We have a pretty huge range in feedstock quality and moisture content, chemistry, particle size distribution. That can be tough. Often disturbances like insects and disease and fire and weather events lead to these kind of spotty, episodic pulses of feedstock availability, which can be challenging if you need a consistent feedstock supply over time. And then often our feedstock supply is tied to other products. We're a byproduct, not a primary product. So we need to be, I think, mindful of that, as well as some of the seasonality and storage challenges. If I could just remind folks to mute their lines. I'm getting a little bit of back chatter on the audio. Thanks. So we've done a lot of work trying to expand markets for forest biomass to try to facilitate some of the forest management needs that we have, especially related to fuel treatment and forest restoration. And one way to do this is, especially in places where we have lost our pulp and paper capacity, which one pulp mill can take a large amount of biomass for cogen of heat and power and for pulp, is to try to think about this in different types of operations, including biochar production as a standalone enterprise or integrated into other types of things like lumber production or biopower or cogen facilities. So biochar, in my group, we've really been thinking about biochar as another product to add to the portfolio of forest products that we can manufacture, especially in co-located settings. So in that context, there are some generalized drivers and barriers to success that we can talk about in terms of new enterprises and expanding existing enterprises into the biochar space. One is integration. So as Gloria mentioned, this cuts across a lot of different sectors. So if we're going to make biochar in the forest sector, we need to be potentially providing products that go into the agricultural sector or energy sector, and that's not always an easy lift. We can think about integration, horizontal integration with other forest industry and manufacturing, other types of products that we might already be producing, and also vertical integration across the supply chain. Is biochar production standalone, co-located with a sawmill, or does a sawmill actually make an investment in integrating their supply chain into kind of downstream products from their residues? Scale is important. Sometimes economies of scale lead us to larger scale production, and other times we need to scale back production to meet our feedstock supply and markets. So scale is an important variable. Competition can be bad in terms of putting up barriers to entry and potentially undercutting us with price competitiveness or the substitutability of other products, which may actually give us opportunities to make different types of products from biochar and cut into other markets. And competition can also provide pressure to innovate, lower costs, increase our productivity to reduce our per unit costs and improve quality. As many of you on this call are well aware, public policy and the policies that are in place can either favor or disfavor bioenergy and bioproducts. And so it's another session we can, as you all have talked about before, the policy environment can make a big difference here. And we're thinking here about regulations, R&D funding, subsidies, taxes, information, carbon prices. I'm thinking about consumer information there, as well as trade organizations and lobbying for policies that might facilitate biochar being integrated into forest industry supply chains. And then local policy and support. So thinking about local support of projects, public acceptance of manufacturing, bioenergy systems, those sorts of things. And knowledge and awareness about bioenergy and bioproducts is huge. So those are just some generic drivers and barriers to success. And I want to talk about some specifics moving forward here. A big objective of the type of research that we've been working on in the Rocky Mountain Research Station and other units within the Forest Service when it comes to biomass, bioenergy, bioproducts, including biochar, is de-risking supply chains. So looking at ways to increase the financial returns on investment in these types of ventures and reducing risk associated with uncertainty in different inputs and outputs, prices, for example, of inputs or prices of outputs, and then kind of the stochastic or random elements of future economic returns on investment in these types of enterprises. And then what the impacts might be high and low on investment to different changes in different important variables. So we can see here just in this simple example, moving a high risk, low return investment on the bottom right to a higher return, lower risk investment on the top left. And an example here would be, reducing risk by having guaranteed access to the electrical grid over a certain period of time for a bioenergy project, for example. At the same time, we provide a price premium for renewable, low carbon energy. One of the tools we use in doing this, and I won't talk in any detail today about this, but happy to talk about it later, or contact me for more resources, is techno-economic analysis. And the quick rundown of this is that we can combine detailed engineering specifications for a specific enterprise, a specific conversion pathway. We can combine that with a benefit cost analysis and use that to compare different project options, different technologies, different business conditions, different assumptions about pricing, or any number of variables. And these are just sample outputs where we have, using the same set of assumptions, compared different types of projects, some of which include biochar production. And we use a simulation approach to look at all the possible outcomes across certain ranges of variables in terms of the net present value of an investment. And outcomes to the right of the yellow line are positive net present value given some minimum return on investment. And then outcomes to the left are negative. And I don't have enough time to talk more about this, but encourage you to think about this as a tool that helps us decide when biochar enterprises are good, bad, or ugly. Let's talk about that. A few things to think about with biochar investment risk. Here's some good things that kind of line up to make an enterprise look likely profitable. One would be a true waste feedstock. So a waste feedstock is one that someone has to pay to get rid of. A proven mature technology, what we call an nth plant design in techno-economic analysis. So this has been around the block. We know it's going to work. Multi-product supply chains. So trying to get value for heat and power, for co-products, for value-added products, kind of a more complex product portfolio that might be insulated from risk in any particular product line. Monetizing non-market benefits, especially carbon benefits for this group, and thinking about how forest industry, biochar supply chains especially, can have a pretty broad menu of non-market benefits. And if we can monetize those, that's huge. Having a price that's high enough to cover the cost of production and profit seems obvious, but not always built into people's plant designs. And offtake agreements and supply contracts to assure that we have a good offtake for our products and a good market for our products. So thinking about what might be on the bubble here, free or low cost feedstocks. So we're going to pay something to get it through the gate, but it's a low cost feedstock. It's a new technology, but it has been tested. It's been piloted. It's been proven in the R&D context. So we might be picking up the alpha unit. Primary products, but we may be using process heat and power. So we might be making a raw biochar product without much value add on top of it, but we can capture heat and power. This might be good for a cogen plant at a forest industry facility. Non-market benefits, we might not be getting any cash value for those non-market benefits, but we might be able to use them as some sort of marketing tool or marketing asset. Maybe prices are uncertain, but we have good transaction evidence on pricing. So we can use that as the basis for our financial models. And then spot market transactions with repeat customers. So we have kind of repeat business. And even though we don't have a secure offtake, we have pretty good confidence that we have a good customer base. And then what's at the other end of the spectrum here? Costly feedstocks, unproven technologies, low value product without much value for anything else or much value added. uncertain non-market benefits. So we don't really have a life cycle assessment on our product. We don't know for certain what the carbon benefits might be. Unknown current or future prices, fuzzy competitive markets. We don't really know where we're going to sell this stuff. That all adds up to a pretty high risk situation. So you'll notice, I'm coming down the home stretch here, and you'll notice I didn't mention much about scale, what scale is optimal, or what might be better for high or low capital or operating expenses, whether or not you should use a mobile, modular, or centralized production system, whether or not you have a very simple or a very complex conversion technology. For example, on the complex side would be a drop-in liquid fuel product along with your biochar, low price or high price for outputs, benefits that accrue to the customer. These are all not as clear with regards to their impact on a particular project. So these really need to be handled very carefully in terms of a financial analysis on a particular project. And so the previous ones are more clear cut. A couple policy connections to make here that I think all of these are probably on your radar already, but now with a little more knowledge about biochar, you can see where they might fit. We can think about direct incentives for biochar production in terms of premiums, subsidies, tax credits, carbon offsets, those types of things. Grants, loan guarantees, especially at the capital expenditure investment phase, are big. Public-private co-investment, partnerships, feed-in tariffs, supply and offtake agreements, payments for ecosystem services, political risk insurance, those sorts of things, and then research, development, and extension. And really the point of all this is to transfer, when we have a product that has public benefits or provides public goods, we can think about how to transfer investment risk to public actors to incentivize those public benefits and make sure we can more efficiently deliver public benefits from these types of supply chains. And this is just some of those examples. And so my take-home messages here are hopefully you have a little bit of optimism in terms of the opportunities for biochar production and use in the forest sector. It's a complex space right now, but I think those of us who have been working on it for a while are seeing some real opportunities going into the next administration and moving forward into a post-COVID world, that we may see more and more opportunity here for integrating biochar production and marketing into existing forest industry supply chains. But honestly, there are risks associated with investment. There's a lot of uncertainty, and some of the things associated with biochar can make investors nervous. And so a big point of R&D at this phase and extension would be to de-risk bioproduct supply chains. And I shared with you one mechanism to do that is really good, high quality techno-economic analysis. And I think that's an example of where research and development can help. So contact me if you want the primary literature associated with some of these studies. I'd be happy to share it with you. And I'll leave you with that. And thanks very much for having me today. And Bev, I'm going to turn it back to you. So take it away,
Great.
Bev.
Thank you, Nate. You just set me up just perfectly. I've got just a few slides to wrap us up, and then we'll turn to discussion. Lauren, am I ready for screen sharing?
Yep, you're all set. Yeah, just you should be able to take it, no problem.
I didn't do it. Okay.
Go to Zoom. Press share screen. There. Press share.
Sorry, everybody. I've got my college-age daughter here as my technical assistant. Okay. Well, so Nate, thank you very much for setting me up just perfectly for this, making a couple of statements that lead right into what I'm going to talk about around how the policy environment can just make a big difference in terms of supporting biochar and helping bring it to full commercialization. So I've been working with a small group, well, we're calling ourselves the Biochar Policy Task Force. And we convened a couple of sessions in December just to try to discuss some of these policies that could enable and that may be currently holding up the further commercialization of biochar. We invited more than 20 groups to join us. And our focus, again, as I don't think I need to explain to anyone on this call, the policy environment has been very uncertain in terms of congressional leadership and just what the appetite might be going into a new Congress for any kind of expansion or additional spending on programs. And so we have focused really primarily on improving or adapting existing federal programs rather than trying to create a broad new program that would require, new funding. At the same time, there's been a parallel effort underway by some researchers to advance a broader biochar research program. So what we've come to is we're busy developing a joint policy recommendations document that we want to share with policymakers, both in the Biden administration as well as in Congress. And we will welcome support. I'm happy to share with anyone on this call who's interested in such a thing, Julie Sibbing, and again, really looking for support. So just to explain a little bit about where we've been talking, we have focused our ideas around 3 areas. Number 1, payments to farmers and foresters. Number 2, support for production facilities and biofuel markets. And then number 3, there's been this parallel research program that the scientists have been working on. Sorry about that. So first, we have spent quite a bit of time talking about existing Department of Agriculture programs, which may be less interesting to the people on this call. But there are a number of programs that serve to incentivize energy production from industries like biochar. So the main thing that we've talked about is really trying to promote biochar in these existing programs: EQIP, the Environmental Quality Incentives Program; CSP, the Conservation Stewardship Program; and the CIG, Conservation Innovation Grant Programs. And I won't read you all the bullet points, but you can see that our ideas, while they're pretty specific, they also are not ideas that are going to cost a great deal of new money. We've also talked about supporting biochar production through the energy title of the Farm Bill and what our ideas might be for future farm bills. Outside of USDA, we have discussed supporting additional funding in upcoming legislation like a stimulus bill, which may or may not come very soon in the new Congress, upcoming appropriations bills, providing grants from the Department of Energy for pilot and demonstration projects, as well as changes to the renewable fuel standard or expansion of the renewable fuel standard as pyrolysis-derived fuels start to come on the market. And then finally, I've mentioned a couple of times this kind of parallel research program that scientists have been working on. And our goals for that would be to launch a 10-year systemic research program on up to 20 sites. Again, we are looking at existing federal research programs, not trying to create a brand new pool of money, but trying to direct existing research programs to support some of these research goals, with the outcomes being able to determine biochar impact on soil carbon sequestration and soil greenhouse gas emissions, and developed research-based knowledge for crop production, for forest health, for landowners, and for farmers. So that's what we've been working on in our policy group. I think we can talk more about all of those things in the Q&A. I'll just put here the contact information for all 3 of us, for Gloria, for Nate, and for myself, and really encourage anybody who is interested in following up, trying to support these efforts, to reach out to me, and happy to try to include you in this work. So that's all I've got. I know that we have started to have some questions in the chat.